Anyway, if you haven't paid yet, then please, if you can pay me after the talk, or otherwise tomorrow. And as you heard, it'll be a bouncer. So unless you pay, you're not in. A very tough bouncer. Thank you. And now for the last session of the talk, it's my pleasure to introduce Fedor Vylegzhanin. Yeah, okay, great. He's going to talk about associated Lie algebras of right-angle Coxeter groups and homotopy theory.
Right, thanks. Thanks to you for opportunity to talk. I had no chances of meeting Fred Cohen, but I still have a story. I had my English exam this June, and I had to translate something from English to Russian. And it could be any paper on geometry and topology, but I had to translate the part of paper of Cohen and Wu on connection between braid groups and homotopy groups of sphere. So it is incredible paper on connections of groups and homotopy, and maybe it was a sign. And my talk is also about connections of groups to homotopy theory, but there won't be a lot of science because there will be Lie algebras of a field of two elements. So what we did with Yakov Verevkin, we found some operations in these Lie algebras which are similar to composition with Hopf element in homotopy groups of topological spaces. And I will try to explain how we apply this. So let me start with definitions. We'll study objects which correspond to simple graphs on M vertices. So we consider just sets of edges. And we can define the right-angled Artin group, which is a free, partially commutative group. So it has generators which correspond to vertices of a graph, and it has relations so that the generators commute whenever the corresponding vertices are connected by an edge. So if you add braid relations to some of these groups, you obtain the braid group. And also we have the right-angled Coxeter group, which is a quotient of right-angled Artin group by the relations so that all the generators are involutions. Also, if you add braid relations to a certain right-angled Coxeter group, you obtain the permutation group. So these groups are important in geometric group theory, but also they arise in topology as follows. If we have a Euclidean space or a Lobachevsky space, and you have a set of hyperplanes which either do not intersect or intersect orthogonally, you can consider the group generated by reflections along those hyperplanes. So if this is hyperplane HI, this is the reflection GI. So clearly these are involutions. And if two hyperplanes intersect, then the composition of corresponding involutions is just a rotation by the angle pi. So the corresponding involutions commute, and we obtain an action of this group on a Lobachevsky space. And we obtain interesting hyperbolic manifolds by taking quotients by freely acting subgroups. So that's why these groups are interesting. And this theory of these hyperbolic manifolds is related to real toric topology and to theory of polyhedral products. So that's when I come from, and this is what knowledge I will try to use. So we study Lie algebras associated to these groups. How do you obtain a Lie algebra from a group? We use the Lie algebra associated using lower central series. So if we start with a group, there is a natural sequence of subgroups called the lower central series. So gamma 1 is just the whole group, and then you define them recursively so that gamma k plus 1 of G is just the commutator of G with gamma k of G. So it's a subgroup generated by commutators of elements from G and from gamma k. It turns out that these groups are normal in each other. Gamma k plus 1 is a normal subgroup of gamma k. And moreover, we have that the commutator of gamma k and gamma L belongs to gamma k plus L. It follows that the quotients are abelian, so we can consider the graded abelian object corresponding to this filtration. So here we have an addition which is induced by multiplication in G. So if I have two elements here, they're represented by elements of gamma k. You take the corresponding cosets. And to add two such elements, we should multiply A and A prime. This is an element in gamma k, and we should take the corresponding coset. But we also have a Lie bracket on this object. This is a theorem, I think, of Magnus. And to obtain the Lie bracket, you should use the group commutator. So it's as follows. We have an element here, which is represented by a coset. A is in gamma k. Here we have an element B. B is in gamma L. So how do we define the bracket? We take the group commutator of A and B. By this property, it belongs to gamma k plus L. So we can take the corresponding coset. And this gives us, in fact, a well-defined operation, which is bilinear, anti-commutative, and it satisfies the Jacobi identity. So the theorem is that it is a graded Lie ring. The fact that this is bilinear and satisfies the Jacobi identity follows from the well-known Whitehall identities, which is a part of commutator calculus. And this is a topic of Magnus Carlsen Solitaire group book. So we can try to compute these Lie rings for certain groups which are interesting to us. So which results are known in this direction? Magnus himself proved that if you start with a free group on M generators, then you obtain the free Lie algebra, the free Lie ring over Z. Where the generators of this Lie ring correspond to generators of this group. We can also study the Lie ring corresponding to right-angled Artin groups, which is a free partially commutative group. So it would be a natural guess that here we should have the free partially commutative Lie algebra. Corresponding to the same graph. It is easy to check that this map is actually well defined, and in fact, it is an isomorphism. This was proved independently by Duchamp and Krob, by Waite, and also by Papadima and Suciu, who gave the most conceptual explanation of this. In fact, if you have a group with such that its abelianization is torsion-free, then you have a good approximation of this algebra by Lie algebra, which is generated by first homology, modulo the relations which correspond to co-multiplication from the second homology to the first homology. And this works for any group G such that first homology is torsion-free. But for right-angled Coxeter group, this doesn't work because its abelianization is a torsion group. This is a direct sum of M copies of Z2. But still, we can try to approximate it somehow. And, well, since it is generated by elements of order 2, here we should consider the Lie algebra generated by elements of order 2. So it is a Lie algebra over the field of two elements. I would denote it by L gamma. This is a graph Lie algebra corresponding to the graph gamma. And in fact, it is a well-defined homomorphism, which is surjective. If it was an isomorphism, my talk would end here, but it is not an isomorphism. And this is, in this generality, it was first studied by Yakov Verovkin, my co-author. So let me list some of his results. Yeah, so first thing that you check that L first gamma is a Lie algebra over the two. phi is a map of algebras. So this is surjective and not injective, and let me show this by an example. We can consider the example of graph with two vertices and no edges. So the corresponding criteria Coxeter group is generated by two elements with no relations. So this is a Lie algebra associated to this. And this graph Lie algebra is a free Lie algebra on two generators. But this is much more smaller. So let me list the graded components. In degree 1, we have two copies, which correspond to x1 and x2 as expected. In degree 2, we have one element, as in the free Lie algebra, which correspond to the commutator. Then we expect two generators in degree 3, x1, x1, x2, and x2, x1, x2. But in fact, we have only one element here. So x1, x1, x2 is equal to x2, x1, x2 in our case. And in all next degrees, we only have only one element. So this is a narrow Lie algebra. It has dimensions of graded components only 2, 1, 1, 1, etc. So on. And in each dimension, you can just use the nested commutator with many copies of x1 and then one copy of x2 as a basis for this Lie algebra. So this example shows that this Lie algebra is much more complicated than in these cases, and it deserves further study. So very often described additive basis, general case in degrees at most 3. And I think this is almost all that we can say about this Lie algebra. So this is almost state of art. And also there are some results in the special case proved in PhD thesis of Robert Brenner. His advisor was Waldinger, and some of this was published in Waldinger's paper. He considered the special case of groups of this form. You take free products of copies of vector spaces over Z2. So some results for these groups are known. And in our notation, these groups are right-angled Coxeter groups which correspond to graphs which are disjoint unions of complete graphs. So this is just a very special case of what we tried to consider. So this is the state of art. And we move on. Let me explain you what have we constructed. And to do that, let me rephrase the fact that this is a Lie algebra over Z2. What does it mean? If I have an element and I multiply it by 2, I obtain 0. So in this notation, it means if I take an element in gamma k, I should multiply it by 2, so I should consider its square. And it is 0 in dimension k. So this means it belongs to gamma k plus 1. So we have this property, which is satisfied in right-angled Coxeter groups, and more generally for any group which is generated by involutions. So suppose that our group G satisfies this condition. If this holds, we can try to do the following. I have the corresponding coset, which belongs in LK of G. I can square the element A, which belongs now to gamma k plus 1, and I can take its coset and obtain an element in LK plus 1. Yeah, thanks. So this is a really natural idea, but you need to verify if this even works, because I could take a different representative of this coset, and I will obtain maybe a different coset here. So it's not that clear that this operation is well defined. And the theorem says that this operation H is well defined. Assuming this property star, and if k is at least 2. Dimension 1, this doesn't work. It's important that k is at least 2. Also, H is additive. And in fact, we have some properties which allow to, in fact, compute this operation for any element of this that you know. So it's additive. Now we only need to deal with commutators in our graded Lie ring. So we need to compute H on commutators. And it turns out if the operation H is defined on element A, then you can just use it on A and then take the bracket. And this is the same. This works if A has degree at least 2. So that's how we deal with commutators of elements of degree at least 2. So finally, we should deal with elements of degree 2. And we need only to work with these elements corresponding to generators, because H is additive. And we can compute them also. It's just a nested commutator of length 3. So H has really nice properties. And this seems new. And in fact, it is pretty much straightforward to prove this theorem if you know how to do commutator calculus. But it's hard to understand why should we expect such operation to exist. But once we can state this theorem, we can prove it. And it turns out that we can compute this operation on any element, so it is pretty useful. So what this has to do, what this has to have in common with homotopy theory. If you have a topological space X, you can consider its homotopy groups. I will shift them by 1. So this is a graded abelian group. If you add the Whitehead bracket, you obtain a graded quasi-Lie ring, which means that this is graded anti-commutative, this is bilinear, this satisfies the graded Jacobi identity, but you don't have the fact that commutator of A with A is 0. But this is still a graded quasi-Lie ring. And we also can precompose elements from here with elements of homotopy groups of spheres. If I have a map to X, I can precompose it with any element in homotopy groups of spheres. I take the composition, which will still give me an element in homotopy groups of X. And I want to take the suspension over the Hopf element, or the Hopf vibration, which I will denote by eta. So we have this operation, which is composition with eta. And it turns out that since in this range, eta is a suspension map, it satisfies the conditions 2 and 3. Because Hopf element is a suspension element, so there is a distributive law for Whitehead bracket and composition with suspension elements. And for some specific space X, it also satisfies the property 4. That's how we discovered it. I'll tell you more if I'll have enough time. But for now, that's all I want to say about homotopy theory. And I just want to explain how we used this operation and its properties to have a better approximation to the Lie algebra we study. Because this is not so good approximation. Clearly, it's not an isomorphism. And we want to have at least conjectural description of this Lie algebra of RC gamma. So first, we obtain that by induction from this formula number 4, we obtain the values of operation H on nested commutators of arbitrary length. So let me have a commutator which is nested to the right. And it turns out that this is equal to the same commutator when you repeat the first index twice. You can consider this as a way to compute operation H on nested commutators. But we use this in a different direction. We use this to remove repeating indices in nested commutators. if I have a nested commutators and some indices repeat, we can use Jacobi identity to let them be close to each other, and then remove this repeat using the operation H. So inspired by that, we consider the following Lie algebra N gamma, which will be a subalgebra of L gamma, generated by nested commutators without repeating indices. So I want K to be at least 1, and all these indices to be distinct. By definition, this is a subalgebra of L gamma. And since K is at least 1, this element is always a commutator, so it belongs to the commutator subalgebra. So I can just put prime here, which means the commutator subalgebra. And since this Lie algebra is generated in degree 1, this is the same as direct sum of graded components of degree at least 2. So this is the object we will need. And I also want to induce the Lie algebra structure on the polynomial ring over this Lie algebra. I add a generator T. So let me just have a direct sum of copies of N gamma times T to the power K. And the bracket is, as you expect, you just take the bracket in N and multiply this part. So just add the exponents. This indeed induces a graded Lie algebra structure on this polynomial ring. I want also T to have degree 1. So this is a well-defined object, well-defined graded Lie algebra. And our theorem is that this is actually an approximation to our Lie algebra L of RC gamma. So we construct a map psi to L of RC gamma. I take an element here. Let me say y times T to the power of K is mapped. I don't have much space here, so I can apply the map phi. And then I want to apply the operation H K times. This is how we define the map psi. And it follows from properties of operation H that psi is a well-defined map of Lie algebras.
What is phi?
Phi is what was used by Vylegzhanin. So it just maps from this graph Lie algebra to our algebra. So xi just goes to xi. It's tautological. And N gamma is a subset of L gamma, so it is well defined. Yeah. So this is Lie algebras. So we clearly see that it does not affect the graded component of degree 1, because this is concentrated in graded components of degree 2 and more. So in fact, we should have the prime here, so that we also start from degree 2. Let me just also say that it's the same of that as the graded sum of degree at least 2. So this is a surjective map of Lie algebras. So this is our approximation to the Lie algebra L of RC gamma. And we also show that in some toy special cases, this map is an isomorphism. First of all, if gamma is just a disjoint union of 2 points, this is also, in fact, easy to see from these properties. And we see that here we have the commutator of x1 and x2. And this is precisely what is N gamma in this situation. And all these elements are obtained by applying operation h. This is h to the power of k applied to x1, x2. So in this special case, this is an isomorphism, and also it is an isomorphism degree k 2 and 3. So we conjecture that it is always an isomorphism. So now we at least have a conjectural description of this Lie algebra. And it seems that unpublished results of Brenner imply that this conjecture holds in the case of chordal graphs. But we still cannot verify it because his proofs are too short. Finally, I want to explain in the remaining minutes why we should even expect some relations with homotopy theory. Well, in fact, it's better to start with the description of classifying space of right-angled Coxeter group. So this is a theorem. Also, I'm sure it was proved by many authors, but in particular, you can find it in the paper of Panov and Verevkin, that the classified space of the right-angled Coxeter group is the so-called real Davis-Andrushkevich space, which is a polyhedral product of a special kind. So this is disjoint union of copies of RP infinity multiplied, which are CW subcomplexes in products of M copies of RP infinity. And we take the union over all simplices of the clique complex of the graph gamma, which means that K is a set of subsets such that their corresponding vertices of gamma are pairwise adjacent. So this is a space which somehow is related to RP infinity, and it's natural to expect that something similar should go on for CP infinity. This is called the Davis-Andrushkevich space, which really matters in toric topology of complex spaces. And these things matter in toric topology of real spaces. And well, in our ongoing research project with Taras Panov and Steven Therio, we tried to do some similar things, starting from the similar identity which holds in homotopy groups of this space. We have some elements, the second homotopy groups of Davis-Andrushkevich space, and a proposition that here we have this intrinsic identity, which is similar to the identity number 4. You can deduce this from like some results from 50s of Barrett and Hilton, and maybe of Barkus and Barrett. And also I want to say that this was actually proved in a paper of Sadok Kalel using Poznikov decompositions of wedges of CP infinity. So it was discovered independently by different methods. So it's nice that homotopy theory has many proofs which maybe can be generalized to different directions. That's all I wanted to say. Thank you for your attention.
Any questions?